Hi everyone, my name is Marcelo, and in this video I'm going to show the results for the final project of the Machine Learning and Pattern Recognition course entitled Fake versus Real Faces Classification, a comparison between models. This work was made in a group composed by me and 4 other fellow students. Our names are listed here. So, I hope you enjoy, and let's dive into it. Over the years, image forgery has become increasingly common due to sophisticated image editing tools and even deep learning techniques for creating fake images, such as generative adversarial networks, the GANs. This problem brought several debates to society and became a topic of many researches around the world, as an initiative to combat fraud, illegal acts, and fake news. With that in mind, we decided to analyze through machine learning models a dataset available on Kaggle and proposed by Udit Sharma. In total, there are 226 megabytes of 2041 images of people's faces divided in 2 classes, fake and real. The amount of image in each class does not differ much from each other, and the dataset is almost balanced. Within the fake class, the images are divided into 3 difficulty categories: easy fake, mid fake, and hard fake. And within the real class, there is only one category, which is real. As a primary baseline, we used scikit-learn library to perform a random forest model. For that, we turned the RGB channels of the images into a gray channel, rescaled the pixels, and separated the data in 2 sets, 70% for training and 30% for test. And during the training, we performed cross-validation with 3 folds. The hyperparameters with the best results for the training are showed up here. We got 61 and 982% of F1 score in the validation set and 6109% in the test set. The confusion matrix was calculated in the test set and also the metrics for each class. For the convolutional neural network, we developed an entire model from scratch with the following architecture. There are 4 convolutional layers with ReLU activation, each followed by max pooling. Then, a flattened layer and a fully connected layer, and the output layer is using sigmoid function as activation. We trained the model for 100 epochs on Keras API, using Google Colab's GPU and Atom as optimizer. We got some really nice values for accuracy and F1 score in the validation set during the training, and the following result graphs. In the test set, we obtained 66.5% of accuracy. For the VGG model, we used an implementation of the VGG16 from Keras with ImageNet pre-training. We froze the network layers and added more layers to be trained at the end. After several experiments with different training parameters, the setup that yielded the most consistent results was to append in the VGG16 a simple set of 2 layers, 128 neurons, L2 kernel regularized with ReLU activation, and 2 neurons with sigmoid activation, respectively. The final results for the model are shown as follows. For the ResNet approach, we chose ResNet 50, a deep network that presents a better trade-off between performance and accuracy in general. As with VGG, the weights were pre-trained in the ImageNet database. The model was trained for 10 epochs using Atom Optimizer and binary cross-entropy loss. The results are shown as follows. Just like in the other models, in this one we also pre-trained the weights in the ImageNet database. We trained it for 14 epochs using PyTorch image models library with Atom as optimizer and label smoothing cross-entropy as loss function. During the training, it was reached a validation accuracy of 73%. The results are shown as follows. For the last model, we used the recent architecture proposed by Google in 2017 in the paper Attention is All You Need. This model from scratch is proveniente from the paper Vision Transformer for small-size datasets, and it was trained using the following parameters. We trained it for 10 epochs using Atom as optimizer and cross-entropy as loss function. The final results are shown as follows. The objective of this study was to compare 5 machine learning models for classifying an image dataset, and in this table we have this comparison being made. The best model for the purpose was VIT, with more than 75% of accuracy in the test set and an interesting confusion matrix. We noticed that complex models will not always give better results, as seen when comparing CNN from scratch to ResNet or VGG. Therefore, even though a suitable model complexity is very important for a hard task like the one studied in this work, data quality is an even higher priority. For more details, you can check the paper for this work, and we finish this video with a very important disclaimer from that. Take a look. That's all. Thanks for watching.